Hello, everyone. Can you hear me, Richard? Oh, very good. All right. We'll just give it a minute more. But in the meantime, if anyone would like to volunteer to to take down the minutes, that would save us some time going through the presentations. That give us more time to do more interesting discussions. Let me put it that way. Are you volunteering, Richard? I will take that as Richard is volunteering. Aha, there you go. Well done. Thank you, sir. So I'll call you out in a moment. And do we need a JavaScript for this? I'm tempted to say no, unless somebody says we should. I'm not going to ask for a JavaScript. Well, if I can get this going right. I'm going to try to share my screen from here. Do you want to share your screen? Yes, I did not change my mind. All right. I think people can see my screen. Yes, I can see it clearly. All right. Very good. There we go. Even better. All right. Let's get started. It's a few minutes past the hour. And welcome to ICCRG, everyone. It's ridiculously early for me. It's 4 a.m. for me. Hopefully, it's a more sane time for many of you. But I'm looking forward to this session. Hopefully, this will wake you up, and hopefully, you'll be engaged as we go through this. So let's just start off with a couple of notes. At a high level, just note well. Oh, hang on. Let me fix this so you can actually see it. There you go. I'm reading Chris's note here. All right, Chris, if you're willing and able to do this, I would very much appreciate that then. All right, we'll go through that in a second. So that's the note well. If you haven't taken a look at it, please do. Please read it before you participate at the mic. I'm not going to walk through all of it in detail, but that, and then a note on the code of conduct that we are bound by the IETF code of conduct. If this is important, please make sure you've seen this as well and read this as well before you participate. And here's the high-level goals for the IETF, and reminder to folks here that the IETF is not a standards development organization. It is a research organization. And with that, I will jump into the agenda for today. So we have several presentations today, and we have an excellent agenda here. with events which are I'll talk about the first one in a moment, but we have a number of presentations, and I hope that everybody stays engaged through the entire meeting. I'll thank Richard for taking down the minutes, and as Chris pointed out on the chat, if somebody wants any comments to be voiced at the mic, please prefix it with the mic in this chat, and Chris has offered to kindly deliver them at the mic, and I'll take him up on that. That is about all from me. I am going to now kick off the first presentation from Rui. Now, this is a slightly unusual presentation in that we are actually going to be talking about a congestion control that is more it's more geared towards data centers. We will kick it off with that presentation. Rui, do you want to? I'm looking here to see. You'll have to come up and ask for camera and mic.
Can you hear me now?
Yes, we can hear you.
Okay.
Let me get you going.
Okay, perfect.
Go for it.
Hi everyone, this is Ray Miao from Alibaba Group. So today we're trying to introduce the HPCC++. So we use HPCC++ to control the congestion precisely, which can achieve near zero queue in our data center, and also maintain very high throughput. So this is our work we published in SICON 2019, and then after that we actively deploy this technique into Alibaba Cloud and with many other vendors. So by that time, we think like we are working with many vendors to want to standardize this algorithm and this design, so we can be aligned in the same setting. So next page. Okay. So the motivation for our design is like today in the cloud, so we design very high performance networking. So there are a couple of motivation for our design. First is the application in the cloud right now is very sensitive to latency inflation. For example, in the EBS, elastic block storage, the SLA guarantee on the latency is 200 microseconds. And some other like key-value application, memory ID application also require sub-millisecond latency. So we think that makes the network become more and more important. The second is that there's many applications such as high-performance storage and the distributed deep learning application that use advanced hardware that can generate the data orders of magnitude faster, and also require ultra low latency for those applications. So that network become a new bottleneck in our system. And then the last part is the new architecture is happening in the cloud. For example, the resources disaggregation, which is separate the compute, memory, and the disk into separate resources pools. So even memory access will go through the network in the future. So in this case, the network become very important and especially require very low latency for those settings. So please, next page. So to support those applications, the silicon manufacturer generate fast ASICs because the traditional software stack cannot keep up with the speed. So the hardware offloading is inevitable. So however, using faster hardware can generate traffic more aggressively. The network congestion becomes a severe problem for our cloud. For example, we running RDMA in our network. We found that there are lots of PFC store and also deadlock events. So we found it's necessary to solve the congestion control problem in this case. Next, please. So we identify a couple of key issues in our congestion control in our high-speed network. The first issue that we observe lots of PFC stall and deadlock events in our RDMA network, and we find that's a cause the stability issue in our network. However, we cannot disable PFC because that will affect the application performance as well. So the key insight for those limitations is that the current congestion control algorithm has a very slow convergence speed. So that's an essential part we want to address. The second issue is that we want to run a mix of application in the same cluster. However, we cannot achieve both high throughput and low latency for different applications. So the essential reason for that is the traditional congestion control algorithm rely on the standing queue. So when the queue build up, the congestion control start to work to react to the congestion. However, when the standing queue build up, the application latency has already been affected. So the last part is we run DCQCN, which is a state-of-the-art congestion control algorithm for the RDMA network, and we found that those algorithms rely on the heuristic to configure their algorithms. So, for example, in DCQCN, they use at least 15 parameter, so to work with the congestion control. So in our case, it's really time-consuming to tune those parameters to work for different workloads. Next, please. So this is why we want to come up with a new congestion control algorithm, which can address our current issue in our production. So the new opportunity we found is that new commodity ASICs, switching ASICs, have inbound telemetry ability, which tells what the status in real time that switch has. So the idea is to use inbound telemetry as a precise feedback for congestion control. For example, in this figure, so the sender generates packets of the user data, and when the packet goes through the network, each hop of the switch will add a telemetry information into the packet. So those telemetry information include the queue length and the TX bytes and timestamp. So to allow us to calculate precisely the extent of the congestion. So the packet continue forward along the path, and each switch will attach the telemetry of its own into the packets. When the packet arrives at the destination, the receiver will generate acknowledgement packets back to the sender while putting those telemetry information into the ACK packet to allow the sender to adjust the sending rate based on telemetry information. So as I said, the most important telemetry information we need is the queue length and the TX rates, so which tells precisely if there's the buffer build up for this particular egress port. And more important, that if there's no queue build up in the egress port, we still can use the TX rate to quantify the occupancy of the link. For example, we can control the link to use as a 95% utilization. So in this case, we can maintain near zero queue because we have a 5% bandwidth buffer to absorb the traffic burst, while still we can ensure very high throughput to saturate the link. Next. So we want to compare our inbound telemetry mechanism with traditional ECN marking. ECN as we know that a single bit notification of congestion is simple and efficient, being supported by many vendors. We view that in-band telemetry is an advanced version of ECN, which provides a fine-grained network load information. For example, Q length, precisely Q length in terms of bytes or in terms of sales, and also transmit bytes, which allows to generate and calculate the TX rates on the egress port based on the TX byte and the timestamp information. The link capacity actually we use to differentiate different link, either it's 100G link or it's 25G link. The benefit or the key insight we get is, first, they can convert to a proper rate. Just one round trip time, we can adapt to the correct rates to avoid congestion. While traditional congestion control, if you rely on the heuristic, every time you cut to half, and after multiple round trip time, you can adapt to the sending rate. The second benefit is we can constantly maintain a near zero Q for low latency, while still we maintain a very high throughput, because we can set a bandwidth buffer to observe the small burst without actually building up a queue. So there are a couple of numeral comparison or overhead of using in-band telemetry. The first one is we use in the paper, we allow each packet to carry the telemetry information, which use up to less than 5% of the bandwidth. That's a ideal case, but in reality, we prefer to query in-band telemetry information per round trip time. In this case, we use a standard alpha 1.0, which is IETF standard INT format. And for those standard, we have 200 bytes metadata for the INT, which account for only 2.5% of the bandwidth. So in this case, we say that because bandwidth is generally abundant in the data center, and we use those small bandwidths for low latency. I think we think it's a good trade-off. Next page. Should I address the question right now, or just later after the presentation?
That's up to you, Rui.
I can talk about that. L4S. Oh, IFS. I'm not quite sure of the detail, but it seems like another standard in the TSVWG, right? So yeah, they propose to use a fine-grained ECN. I'm not sure how to compare it, because I remember L4S targeting on the wide area network, and it's focused on the switch support to improve the traditional ECN, while we're focusing more on the data center environment, where the INT feature can be supported in those switches that can give us more information. And especially for the data center, the bandwidth is abundant, so we can use those bandwidths to send the telemetry information. Is the protocol intended to be used on the internet? So right now we're focused more on the data center environment, because you know because the telemetry information is more directed to the data center or cloud provider. So those low-level congestion information or traffic load information is very sensitive to to the network operator. So if you want to use the internet-wide environment, then the one issue is maybe explore those detailed information to the other user. Maybe there are some privacy issue.
Rui, just a high-level point. The chat will keep going on, which is a
Okay,
good
I
thing.
see.
You may want to finish your presentation and then see if people want to answer questions at the mic, or you can continue the conversation on the chat after your presentation as well.
Okay. Thank you. So
Yeah.
we highlight our design. So the key design is using in-band telemetry as a precise feedback. We can quantify the condition and precisely and react to it precisely. So this gives us three benefits. First convergence. So the sender know exactly how to react to the condition, and it can adapt to the precise rate in just one round trip time. The second is we can maintain near zero queue because our feedback doesn't rely on the queue length. Not only rely on the queue length, but also rely on the TX rate. And also in our case, we have few parameters. We only have 3 parameters, and those parameters is not related to the performance, it's just a trade-off. So in this case, we don't need any heuristic to infer the status because we can directly get what's going on in the network. Next. So this is the preliminary result from our SmartNIC implementation we deployed. And as we see that in the left figure show that the axis is a different flow size. The y-axis is a 99 percentile normalized flow completion time. Actually, in this figure, the lower the better. The lower means the lower latency. And we compared our design with DCQCN, the purple curve, which is the default congestion control in RDMA. And as we see that for those small messages, we can reduce the latency by 25%. And even in a median like 200K flows, we can still reduce the latency by 55%. In the right figure, we show that overall in the experiment, the distribution of the queue length in the switch. And as we see that in the HPCC++, we say that even in the 99 percentile, the queue length is only 23 kilobytes, which translates to 7 microsecond queuing delay in 25G link, which demonstrates that we can achieve ultra low latency while maintaining near zero queue. That's all for my presentation. I'm happy to take any questions right now.
Thank you, Rui. I see Vidhi at the mic. Let me. Okay. I thought this was.
Me? Sorry.
There you go, Vidhi. Yes.
Thank you, Rui, for the great presentation. I just have a question in the graph that you were showing. Just the previous slide.
Okay.
Can we switch to the previous slide if that's okay? So the first graph, why does the latency becomes normalized like for the purple and the green? I was imagining in my head that it would always stay low. Why does it become the same at higher
At a higher flow size?
Right.
Oh, yeah. So for the higher, which means the flow size is larger than 1 megabyte, for example, is a throughput oriented for those flows. And those flows maybe need tens of rounds to finishing.
Right.
So,
but don't we have much better feedback? Is this assuming some kind of loss, or is it like a real-time test? I didn't get the environment.
Yeah,
How
yeah,
it's
it's a real
Vidhi, just
time
very
test bed.
very quickly, Vidhi, there's echo coming out of your mic.
okay.
Yeah,
Let
please
me
mute
mute.
if you're not speaking. It might be the best way to do this.
Yeah,
Go on,
so
Rohit.
yeah, so we keep the utilization to 95% tage. In this case, we have a 5% bandwidth headroom to absorb small burst. So in this case, the short flows, like the number in the left, have very low latency because we don't build up the queue. However, if you look at the very tail of this figure, we actually perform worse than the DCQCN for those long flow because they can use 100% throughput. We only use 95%. That's a difference.
Thank you.
Ignacio, you're up next.
Hi. We just comment on the chat that this idea is similar to a protocol discussed in IPPM group, the EAOM protocol. It's different because here you are measuring the queues, which is directly related to traffic and congestion. But there are several issues that you can find when you try to do this in every step or you flow. The question is if you already knew this protocol that we are discussing IPPM, and how do you think that this, the second question is, how do you think that it's possible to use your protocol when not all the steps inside in the path, in the flow paths are collaborating with your protocol? Because if you are thinking that this protocol is developed very slowly, okay, you will get this situation. Thank you.
Oh, you mean, I don't get it, the related word. Is you mean IPVM or IPPM? So to answer your question, I think for HPC++, we need a separate queue for our protocol. Just like ECN, you need a separate queue for ECN and for TCP traffic as well, right? So we need to have a separate queue for HPC++. If you don't use the HPC++ for some of the end hosts, you might have to use a different queue. So we use the queues in the switch to separate different protocols.
Let's continue this one on the chat if you would like, Ignacio. Stuart, you're up next.
Hi. Just a quick comment. I think I understand the confusion that led to Vidhi's question. And this happens a lot when people use the terms latency and delay interchangeably. This graph is not showing the latency in the sense of the per packet round trip time. It's showing the total completion time for the transfer. So when you have a really large transfer, many round trips, the actual per packet latency becomes less important.
Yeah.
That's why they converge.
Yeah, so the left figure
more than per packet round trip time.
Yeah, the left figure shows the flow completion time, which means the translation delay for this flow. How much time for the network transmit this particular flow? So, yeah, certainly need a couple of round trip time. For the figure in the right, it actually shows the delay of the network, because the left side shows the CDF of queue length, and so if you add about the transmission delay, this is the queuing delay, right? So this is a queuing delay distribution. You can translate into that.
Yeah, my comment was just because Vidhi was asking on the left graph why the lines converge above 2 megabytes. And anyway, that was my comment. Just
Oh, I see. Yeah.
help clear that up.
Yeah.
Thanks.
Yeah. Thank you.
Thanks, Stuart. Chris, you're up.
Relaying for Ayush. What's the difference between the HPCC presented at SIGCOMM and the HPCC++, which is being presented here?
HPCC is more academia like a style. There are a couple of differences. First one is we use per packet INT, but in the production, once we after the publish on SIGCOMM, we work on the vendor to deploy this in our production, and during this procedure, we'll accumulate a couple insights or experience from deploying this protocol. That's come with HPCC++. So it's more production ready, and it's standardizable protocol. Like some of the design is too artificial in the SIGCOMM paper. So in the HPC++, it's more practical and design, and it's good to align with different vendors, because we when we deploy this protocol, and then we actually talk to different vendors to implement these protocols. We talk to the NIC vendors and also talk to the switch vendors individually. So that's come with we want to standardize so that we don't have to talk to each one individually, but we're talking in a common language. So that's why we come up with this HPC++. There are a couple of a detailed design in the draft. That's quite different with the paper version.
Yeah, I would encourage people to read the draft as well. Roland, you're up next.
Hi, just a quick question about multiple bottlenecks. So did you consider multiple bottlenecks, or are they occurring in your setup at all? In the network telemetry data, does it allow you to identify the particular bottleneck for a specific flow?
In the paper version, we consider the multiple bottleneck design, and we carry INT information for each hop, so that we can actually know where is the congestion. And we have a complete design to consider all the bottleneck, and we actually can change the sending rate. So both based on different policy. So we can say, like, under the multiple bottleneck, we can achieve maximum fairness or proportional fairness, or something between that. It's alpha fairness we can achieve. But later in the production deployment, we found that the simplest way is just to do the maximum fairness. We don't store, because in multiple bottleneck case, we need to stop all the information for each hop. That's actually costs more resources, but the benefit is very limited. The benefit is just how fairness we can achieve, what fairness we can achieve, and how quickly we can adapt to the fairness point. But actually, we care more about utilization convergence, which can avoid congestion, but we don't care much about fairness convergence. So because the flows are actually very short in our case, we don't consider. So that's why we make a very simple design.
Okay.
That work with the multiple bottleneck case.
Yeah, thanks.
All right. Thank you so much, Rui, for that. I'll encourage. This is a presentation which was in part. There was some discussion on the ICCRG mailing list. People seem to be interested in discussing and engaging in data center congestion controllers. So if people are interested in that, I would encourage you to engage on this more on the mailing list. And I'll also encourage Rui to bring these up on the mailing list. We are trying to gauge how much interest there is in topics around DC congestion control. If there is interest, please bring it up on the mailing list. It'll be good to know.
Yeah, thanks. I have already copied these comments. I will reply in the email. Thank you, everyone.
Excellent. Thank you so much, Rui. With that, we will move on to the next presentation of the day. Let me see if I can. Robin, you're up.
Yeah, mic is on.
Yep.
All right. So for those people who've seen this yesterday, don't worry, it contains a lot of new information, so you don't get too bored. Next slide, please. So QLog stands for quick logging, and its project started about 2 years ago when we identified that the new protocols would probably get quite complex to actually analyze and debug in practice, and we would going to need some advanced tooling to do that. What you would typically do for something like TCP, for example, next slide, is you would take a packet capture somewhere in the network, right, and then analyze that using something like Wireshark, for example. This is still possible for Quick, but quite a bit more difficult because, next slide, Quick, of course, encrypts most of its transport level metadata as well. So to do this, you would have to store the entire packet capture, including the very large payloads, and also the TLS decryption secrets, leading to obvious privacy and scalability issues. There's, however, a second, more long-standing problem with the typical way that we do this. Next slide. Which is, of course, that a lot of protocol information isn't always reflected on the wire. And that's, of course, always the case for congestion control information like the congestion window, which I don't have to tell all of you. And so to solve these problems, or to try and solve them for Quick, we propose a different approach. Next slide. Where the idea is, instead of doing a network-based capture, let's log this information at the endpoints directly from the implementations. Obviously, have all the salient data right there available, and they can easily leave out the privacy-sensitive parts. This is, of course, not a brand new idea. Many implementations have some kind of debugging output, for example. But the idea of QLog is to have like a single format, a single schema that all the different implementations can use, making it easier for us to create reusable tooling on top of that. And so next slide. QLog really is not rocket science. It's relatively simple. Currently, we just map this into JSON, and we define how, for example, a received packet containing an acknowledgement frame should look like, or indeed on the right side, what you should call the variables related to, for example, congestion control updates. Using this type of log as input, we were then able to create quite a few, indeed, reusable tools. Next slide. Which are available in the QVIS tool suite. One of those is, for example, here the sequence diagram, where in the middle you see the packets going over the wire from client to server and vice versa, and their contents. But on the right side, you see implementation side updates, including, for example, when a probe timer was set, or indeed when the bytes in flight was updated, allowing for very fine-grained debugging of these systems. Next slide. A second major tool that we have in QVIS is a kind of, you could call it the TCP trace, but then for Quick, where because of this approach, we don't just show the data and the acknowledgements and the flow control, we can also show congestion window, bytes in flight, and also the various round trip time measurements that are used internally immediately. And so for me, as definitely a non-expert in congestion control, I really like this type of thing where you see the very clear correlation between the congestion window rising and the RTT going up with that as well. It's very interesting to see this so graphically. Next slide. This tool has then been used by quite a few implementers. For example, this is from a blog post from Cloudflare, who explain in detail how they've used this to debug their initial Cubic and HighStart implementation for their Quick stack. Next slide. But it's also gone beyond initial deployment, initial implementation debugging. For example, what Facebook has done is they have deployed QLog at scale in their data centers as well, and so they've been able to find quite a few relatively quick specific bugs in their setup that were previously missed in lab testing that only really surfaced during their deployment. For example, one of the things they had was that they were underestimating bandwidth during the zero RTT phase because they were relying on previously acknowledged packets, which during zero RTT you do not have previously acknowledged packets, at least not ones containing application layer data. Another one that is in a very interesting paper that I'll link to on the bottom there was that in Quick you change encryption levels, and that is accompanied by you can do that with implicitly acknowledging all the packets from the previous encryption level. And the way they did that was they mismeasured the RTT there. So RTT was suddenly much lower than it actually was because of the implicit acknowledgements, again causing a wrong bandwidth estimation from that.
There you go.
Okay. Okay. So the thing is that previous slide, please. So the thing is that this has been used not just by the experts or the people that knew what they were doing to great effect, but I think in Quick we had this very special situation where you have a lot of Quick implementers that are really not congestion control experts by themselves, and they have to try to make something working based on the drafts and looking at other people's code. And I think this kind of tool and approach has really helped them to get their things at least somewhat working. Next slide. And I think that's one of the main reasons that Qlog has found quite a bit of support within the Quick community. Most of the implementations actually output this directly as well. And as I said, Facebook is using this extensively in production. And it's because of this that the format has shown promise and the tools seem useful that we are now moving for adoption of this work by the Quick Working Group. Next slide. Which is intended to happen somewhere over the next months as part of the Quick Recharger. One of the goals there is to flesh out all of this for Quick. We have some basic congestion control stuff in there, but for example, Facebook, they have added a lot of custom events as well to help them better debug their custom setups. And so it's going to be interesting to see how we need to update the default Qlog stuff to match that. The second main thing, and one of the main reasons I'm here today, is that we're also trying to figure out if this can be extended to more than just Quick. Logically, of course, things like TCP or the multi-path versions of these, or things like mask or general tunneling, also, of course, have to deal with aspects of congestion control and can get quite complex. And we hope this approach could be useful for those things as well, with the ideal goal of creating tools that can be reused across protocols. Next slide. So we also have a few proof of concept projects around that. For example, for TCP, we've been playing around with eBPF and using K-probes to get this kind of information bubbled up from the kernel. We then combine these with the raw packet captures from Wireshark to get like a full view of what the TCP stack, for example, in Linux is doing, which has led to some interesting observations. Next slide. We've also been playing around with this for multipath Quick, and we have an ongoing project looking at this for multipath TCP as well, where we tag each event with a specific path ID, so we can split them out later and have comparison between the different paths, of course. So it shows definite promise. It looks like we'll be able to do this. However, we are also running against a few challenges or bottlenecks. Next slide. For example, we've recently started a major push towards actual performance testing of Quick stacks. And Qlog currently, as I said, is JSON-based, which is flexible, but it's also not super optimized, for example, in terms of file size. And so testing performance on gigabit networks has turned out to be quite difficult to scale. There are, however, other people, like, for example, Nick Banks from Microsoft. They are using a custom similar approach, but they are using a more optimized format and custom tools where they are able to ingest much larger log files and much more information to help debug this kind of high performance scenario. So I think a general approach is good. We just need to look at how we implement it specifically. And that's one of the discussions that we will definitely have for QLog. One of the problems that I have there is kind of the main puller of this thing. Next slide. Is that again? I am not I'm not an expert. I don't implement these things myself. I don't test them. I don't do research. So I don't know what the typical way of working for this is, either in research or in actual deployment. I've seen things like this come along here in this research group. This was from a couple of meetings ago, which seems fantastically interesting as a tool. It's unclear, for example, here, I don't know if you can actually log the individual congestion control windows or if that's even useful, right? And so next slide. The fact that I need more feedback became obvious earlier in the early days when I talked to Jana, asking, how can we improve this TCP trace for Quick? And he said the simplest thing you could do is add this type of thing, a ruler, where I can just drag and drop across the data line here, and it shows me about what the data rate was and how long it took, which is really, really simple to implement. I think I did it in about 1 hour, and I would have never thought of that myself, that would actually be useful in practice. So it's that kind of input that was really, really useful for me to optimize this tool. Now, where am I going with this? Final slide. Because, of course, the IETF does not standardize tools. And I don't want to make this all about the tools, but I do think that if the goal is to have a format that can be reused across implementations and protocols, and that we can then build reusable tools on top of, that it might be a good idea to start from the tools and then work our way backwards to make sure that we are not missing things that are very useful in practice or are actually being used right now. So we're looking for feedback now on formats and ideas you might have had there, and also some things that you might have had as input from tools. Most of this work for practical reasons will happen in the Quick working group, even though we're also looking for other protocols as well. And we will, of course, have some very good input already, because there are a lot of knowledgeable people involved in Quick with this as well. But extra feedback and opinions are always welcome there, or using the GitHub, or of course, right now, as I'm interested in hearing feedback and questions. Thank you.
Thank you so much for the presentation, Robin. We have time for just a couple of quick questions, but I want to quickly say that I'm grateful for Robin for presenting this here, and of course for the work that he's doing. This is super, super useful for Quick, but as he points out, it's super helpful for transports as well. People who wanted to do and use tooling that's more modern, so to speak, will find this to be extremely useful. Okay, Jonathan, you're up.
Thanks. I just wanted to ask what sort of compression algorithm you're using to get the 18 megabytes.
That's just normal zip. Normal
Just gzip.
Oh.
Okay, so presumably a more advanced compression would get it down smaller.
Sure, and for storage and transfer, that's fine for now, but it's mainly if you want to load this. For example, Archivist tools are all web-based, and your browser really doesn't like you uploading a gigabyte JSON file, or downloading the compressed version and then having to unzip it in the browser is also not something it likes to do. So.
Yeah. Okay.
All right. It looks like we don't have anybody else in the queue, but oh, Jake, you're up. Richard, okay. I'm going to close the queue after Richard, but Jake, you're up next.
Yeah, hi. I do think this looks very interesting. Has anybody started doing anything with this for TCP? Like, this seems like it does have obvious applicability.
Not concretely. Like, we have the proof of concepts, but those are more like research projects. I do know that people at Facebook and Google have shown interest in applying this to TCP as well, and I think even Apple as well, to doing that. But I don't know of any concrete efforts yet, but I'm very interested in hearing from people.
Okay, thanks.
So I just wanted to basically chime into the same horn here. And I think it's very interesting to have a standardized way to log these congestion control internal events, especially useful for TCP, obviously, because right now, at least I am faced with at least 3 different approaches how to diagnose and troubleshoot TCP, and none of them are standardized, so they all need their specialized tool sets. They may need recompilations of the stack and so forth.
Thanks for that comment, Richard. I'll say that at a high level, just 2 quick points before I let Robin go. One is that the QLog tool, the QLog schema is different from the visualization tool. And that's actually quite an important distinction here to your point there, Richard, which is that if you want to extend the schema to include more events in TCP and so on and so forth, that is an excellent that'd be very useful work, I think. I'm speaking for Robin here, but at the moment, in the quick working group at least, this is going to be taken up, and the focus is going to be what needs to be logged for quick, not for other protocols. But if there are extensions that you need to make, or if you want to extend the schema for the future, that work would be very useful to do now, because I imagine that if you want to adopt this sort of work in other working groups, then having that work done before it gets there would be very useful. All right. I will thank Robin for his presentation. And Martin, you get to jump into the queue and say something.
Yeah, hi. Thanks, John. I just want to say, yeah, as responsible AD for TCPM and TSVWG, I think I would be very interested in drafts for events in those protocols and other transport protocols appearing in those working groups to standardize in the QLog framework.
Thank you, Martin, and thank you, Robin.
Thanks all.
To the next one. Anna, I think you're up. I should.
Okay, thank you, Jana. So I am going to talk about the congestion control in the multipath context. And this is work that has been done as part of our work on multipath DCCP. But what I'm going to talk about today is also applicable for other protocols. So the general problem of congestion control for multipath. And this is joint work with colleagues at Deutsche Telekom, City University of London, and my colleagues at Karlstad University. And in particular, the results that I will talk about today is from our PhD student at Karlstad University, Markus Pieske. So next slide, please. So first, a little bit about the background and context. So we are working on multipath DCCP as a multipath solution for transporting general IP traffic or UDP traffic. And this framework is using DCCP as the protocol. So you have one DCCP tunnel per path. And the 2 main use cases that we have in mind for this is in the context of 3GPP and access traffic steering, switching, and splitting architecture that is being defined there for combining cellular and Wi-Fi networks, and also for the hybrid access use case in home networks where you combine the fixed and a cellular link for better performance. Next slide, please. So then let's look at the problem that we then encounter if we have this type of multipath framework, and this is generic for the protocol, as I said. So this tunneling solution, of course, results in nested congestion controls, and this can also be a problem for single path tunneling. But when you move into the multipath context, this encounters, of course, an added complexity. And in our work, we are using uncoupled congestion control over the two paths in all the cases, as the use cases here, we don't see the need for coupling the congestion control, as the idea is to use the two paths and to be able to aggregate them and use them for the better performance, and we don't expect the fairness issues to come into play here. So you see the general setup on the picture here. You have a UE, and then you have a proxy or a tunneling endpoint, where you in this figure have a downlink transfer. So you have the scheduling component in this end, and then you have two paths, two multipaths with a congestion control, a reordering component for the packets, and then you have also the congestion control from the UE and to the server. Next slide. So this scheduling and reordering components will have a very large impact on the performance in this scenario. So in this results that I will talk about today, and also for a lot of the work we have done here, we have looked particularly at the cheapest path first scheduler, or the strict priority scheduler. So you have a preferred path, and you send data on this path whenever you have space available in your congestion window. And it's only if this preferred path is not available that you start to use your other paths. And this is also, of course, we think a quite reasonable scheduler for the scenario that we are targeting, because you may, for instance, want to use your Wi-Fi network and then only use your cellular quota if the Wi-Fi network does not provide sufficient performance, or you use your fixed network in the hybrid access scenario and then use your cellular network for improved performance when needed. So this is a scheduler that can have benefits both from the user perspective and also from the operator perspective. The reordering component can also have different functions, and I think Marcus will talk particularly about reordering in the next talk. But in the work I'm presenting here, we're using an adaptive time limit for the reordering to determine if to pass the packets on or not, as we may not have a reliable transfer also over the tunnel paths. Next slide, please. So I mentioned that if we move to the multipath domain, we have some additional challenges for the congestion control in congestion control. And particularly the challenge in this scenario is to be able to aggregate the capacity over the two paths. So you're using one path as your preferred path, and the challenge then is to actually be able to also use the second path when needed. And in particular, the end-to-end congestion control may react before and slow down before you are able to actually start to utilize that path. If we take the next slide. And here we have an example of this. So what you see in this graph is a time sequence of 4 different transmissions stacked on top of each other. And for each one, you see the green throughput is for the preferred path, and the red throughput is for the second path. So up at the top of the topmost scenario, you see that things work as you would like it. You have capacity using both the first path and the second path. The second scenario from the top, on the other hand, does not work well at all. You're not able to use any of the second path, so only the capacity on the first path is actually utilized. And then we have 2 examples where you kind of manage to use some of the capacity of the second path, and in general, the use here is going up and down a bit. And this is experiments with 4 different configurations that shows how different the outcome can actually be here, depending on a number of parameters that impact this performance. Next slide, please. So the results that I'm showing here is using a user space implementation of this multipath framework. So there is also a kernel level implementation developed by the colleagues at Deutsche Telekom available that Marcus presented last IETF in the TSVWG session, some measurements from there. But here we use a user space implementation, which of course offer then quite a lot of flexibility in trying out different protocols and different configurations. And this user space program do you hear me? Okay, something seemed to have happened there with the...
Good luck.
I'm back. Okay, when did you lose me? So I was explaining that we are using the user space framework for this experiments, and this offers then a lot of flexibility in how to try out different scheduling methods and different protocols. So in this framework, the packets are captured through the Linux Tune device, and then the framework encapsulates the packets with information like the path sequence numbers and the timestamps of the packets. And then packets are scheduled over 2 single path sockets. So this means that the framework as such is not tied to DCCP. It also allows us to use other protocols as tunnels. So in the experimental results, we have both DCCP and TCP in the experiment that you will see in the next slide. So this is the setup of the experiments. On the end-to-end path, it's the IP tunneling where we have TCP on top. So we have used TCP cubic and TCP BBR, and in the tunnel, okay, so I think maybe I will turn off my video because this maybe is messing up with the... Okay, so as I said, for the tunnel, we are using both TCP, TCP Neurino and TCP BBR, and then we are using DCCP with CCID2, which corresponds to Neurino, and also a new CCID, CCID5, which is an implementation of BBR style congestion control for DCCP. And we have some base delays for the 2 different paths on the multipath, and for the added delay to the server, 20 milliseconds on the preferred path and an additional 20 milliseconds to the server as a baseline, and a symmetric path as a baseline with 40 milliseconds to the second over the second path, and the same bandwidth and same queue configurations on both paths. So next slide, please. So now some example results. So short here stands for the basic configuration, and what we see here is the combination of different congestion controls on the end-to-end path and then in the tunnel, and the results are relative to the performance over a single path. So you see a percentage of the flow completion time for downloading a large file here. So if you're below 100%, you have gained performance as compared to the single path case. And you can see here that the performance varies a lot depending on what congestion control combinations you use. In general, BBR is performing better as a tunnel protocol, and this is as BBR reacts faster when you start to experience congestion, and there is also less loss over the tunnel with BBR. And you can also see that the BBR at endpoints with Reno in the tunnel performs very poorly here, because BBR reacts before the second path is used. Next slide, please. So here we have another scenario where we look at the impact of where you put the tunnel endpoint in relation to the server. So the short near scenario here, the proxy is closer to the UE, and you have more of a difference between the round trip times end-to-end and over the tunnel. Whereas the short distance, then the proxy is further away and closer to the server. And you can see that this placement of the tunnel endpoint also has a large impact on performance. And having the proxy closer to the user, to the UE as expected, is typically beneficial, because in this case, you have more of a difference between the two control loops when you have more difference in the RTTs. And in particular, you can see that if the two RTTs are similar, then BBR over BBR performs quite poorly. Next slide, please. And this is taking a little closer look at this particular scenario of BBR over BBR. So what you see on the x-axis here is the end-to-end RTT, and on the y-axis you have the portion of that RTT that is within the tunnel. And you can see very clearly here how this has an impact on performance. And if you have a similar RTT between the two paths, then BBR here is reacting with a similar attempt to fill the bottleneck and is not able to move the traffic over to the second path. Next slide, please. Okay, so to summarize, the congestion control and congestion control aspect has a lot of impact on the performance on the multipath tunneling problem, and there's a lot of factors that interact here. So the results that we saw here were particular to the scheduling mechanism of cheapest pipe first, and it also has a large impact what the ordering mechanism you use. The different congestion controls have quite different interactions. The placement of the proxy, of course, is also quite important, as well as the path characteristics. And if we should have some first general conclusions from the work we are working on, we can see that overall BBR performs better than Reno as the congestion control for the tunnel. And having the proxy close to the user, as expected, is typically beneficial. And we are actively working on this, playing with the different parameters and analyzing the various interactions. So I hope that more results will also be coming. And with the next slide. And there are also a number of drafts that are related to this presentation. So there's a draft for the multipath DCCP protocol. There's a draft related to the framework, multipath framework, some draft related to how to send DCCP efficiently over UDP. There is a draft on reordering that I think Marcus will talk about next. And there's also a draft on multipath schedulers. And with that, I am happy to have questions.
Thank you, Anna. Let's keep this quick because we'll have questions after Marcus's presentation next as well. I'll close the mic line here after Gauri, but Martin, you're up.
Thank you, Anna. This is very interesting. How applicable do you think these results are to non-multipath scenarios that have congestion control in congestion control, like mask?
So, I mean, the particular problem of using the second path, which is the main challenge here, will not happen unless you have multiple paths, of course. Some of the aspects that we see here, for instance, the relation between the different control loops in terms of RTT and the impact of what the congestion controls you use in the tunnel versus what you use end-to-end, will also come into play in the single path context, but the results are not directly transferable, of course.
Gauri, you're up next.
We don't hear you, Gauri.
On slide 11, I was curious with your heat map and how this would play out if there was a much larger RTT at place. You know, so can you just talk me through a little bit more about what's going on?
Yeah, so what you see here is that the end-to-end RTT is going from a very small RTT from, you know, I think the smallest value used is 5 here, and up to about 100 milliseconds. And then on the y-axis, you see what portion of that RTT is in the tunnel. So as you go up on the y-axis, you have more and more of the RTT is inside the tunnel, which means that the proxy is further away from the UE.
Is the blue hole around 20 just an artifact of the analysis?
The blue hole around 20? I'm not sure what you mean up in the top there.
Yeah, the top.
Yeah, I think that's just a random effect. So I mean, what we have done here is we have sampled this space with the number of measurements, and so each measurement point here is you know, not repeated many times. It's like 400 samples over the space to create this heat map. So there is some noise in this graph, of course, but you can see quite clearly that the blue space is quite separated from the red. So you can see quite clearly the impact of the two control loops and the difference between the RTTs in the two cases.
Thanks. That's really nice. Thank you.
Thank you so much, Anna. We'll move on to the next presentation. This would be the same space, but I'm going to bring this up. Marcus, you're up.
Hi, can you hear me?
Yes.
Very good. Yeah. So I want to talk today about the multipath sequence maintenance. What this means, I will elaborate in the next slide. So next slide, please. Yeah, starting with how multipath typically works, which components are usually employed. So let's have first a look into the picture. So on the left, there's a sender. On the right, you have a receiver. And in between that is now very much related to multipath. You have at least two communication paths. And on sender side, you have a scheduler which is responsible to distribute traffic across the multiple paths. So you can have different logics for this, and you will find a number of logics already described in the ICCRG scheduler draft. While on the receiver side, you probably have a reordering mechanism. So here it's called reordering queue, and that is exactly where we want to focus on today, on how can we ensure the sequence maintenance when it comes to multipass. Between sender and receiver, a multipass network protocol takes responsibility to allow the communication between sender and receiver. And typically, in such scenarios, when it comes to heterogeneous environments, you have a latency delta between the multiple paths employed in the communication. And that is exactly the issue where I want to talk about. So with this latency delta, you can imagine when we simultaneously use the two paths. So maybe we send the packets in a round-robin fashion. That will cause out-of-order delivery on receiver side. And with that, it completely differs from the characteristic of a single path communication, because in a single path communications, you're only dependent from the latency of the single path. So keeping it short here, having a latency delta between multiple paths causes some trouble, and services with a certain expectation on data sequence and consistency will experience issues. If you look at IETF, we see there are multiple multipass protocols defined or available as a draft. That is multipass TCP, multipass DCCP, multipass QUIC, CMT, SCTP, and so on. And would be interesting to see in the next slides how they behave when it comes to out-of-order delivery and which mechanisms they have implemented to overcome this. Nevertheless, typically scheduling and reordering are not part of the protocol specification, and it's left to the implementers to take care. And that might cause trouble if an implementation is dependent on protocol mechanisms. We will come to this in the next slides. So for MPTCP, reordering is simple to view the strict reliability of TCP. So it's a just to wait approach on the receiver side. But if you look into the next slide, then we see that there are a number of multipass protocols which claim to provide no strict reliable in-order delivery. And that is, for example, the multipass DCCP. It's also the combination of concurrent multipass SCTP combined with the partial reliability functionality from SCTP. It's also the multipass QUIC when it becomes combined with the QUIC datagram. So from today's perspective, I think they should consider sequence maintenance in their design, but from my feeling, that is not completely given right now. So for the three protocols I mentioned on this slide, the DCCP, SCTP, and QUIC, when it becomes combined with the unreliable transmission, then strict reliability is not an option, obviously. And the solution, if we talk about sequence maintenance, will be a trade-off between maintaining the data sequence without interrupting the data flow. A special challenge in this scenario is when it comes to packet loss, and I think it's likely when we talk about multipass transmission that we will see packet loss to some extent, and then this is always combined with the question, so how long do we have to wait in a potential reordering mechanism on receiver side, and at one point, at which point in time we can assume that a packet is really lost and we have not to wait for it any longer. So during the multipass protocol design, this has to be considered, and possible measures like different sequencing schemes. So for example, a sequencing scheme for path and separately for the multipass connection, or a sender receiver signaling have to be taken into account. I will come to this in the next slides. Yeah, with this draft we have available as ICCRG, the multipath reordering draft now in version 2, we claim to cover all these aspects and provide guidelines for design and implementers of multipath protocols. Next slide, please. Yeah, okay, let's have a deeper look into what we have specified so far in the draft. So we discuss several mechanisms to support smooth and adjustable in-order delivery for multipath communication. In this draft, scheduling is out of scope, so scheduling maybe also provides some measurements to overcome out-of-order delivery on receiver side, but we see this rather as part of the scheduler draft available at ICCRG. So we discuss, for example, resequencing mechanism with which we want to keep the generated sequence of data at receiver side. And there we discuss multiple functionalities or multiple logics. So the first is the passive one. So we just forward packets as arrived. For sure, that will not reorder at all. Then we have the exact mechanism that is similar to TCP and provides strict reliability. Another mechanism is the static expiration. That means we wait a certain time for missing packets until we assume a packet loss, and any packet which arrive in time will be reordered. Adaptive expiration is similar to the static expiration, but we do not have a fixed time threshold, so we dynamically adjust the time on how long we wait for a missing packet, depending on the RTT, for example, or the latency on the path. Then we have delay equalization, strictly spoken, that is not a reordering mechanism, that just delay the faster packets to match the latency of the slower path. And last but not least, we discuss fast packet loss detection. That is probably something which can be combined with the other logics, and that leverage the path and connection sequencing to have a very early idea about if a packet is lost or delayed. Next slide, please. Then we have two other areas identified which can help to overcome out-of-order delivery. That is recovery and retransmission. In the recovery area, we see that we can overcome packet loss when we spend redundancy, and in that area we see forward error correction, but also network coding. And when it comes to retransmission, so overcome packet loss by retransmission, we also see three different mechanisms which can help here. On the one hand, we have the signaling, which is, for example, used in TCP or DCCP to signal outstanding packets to the sender. Anticipated means we predict a beneficial early retransmission for the reordering purpose. And last but not least, we have the flow selection, so the ability to retransmit packages on a path different to the original one, if this supports the reordering. As I said, combinations of mechanisms are in principle possible and most probably useful. Next slide, please. Yeah, first of all, I want to invite you to contribute to this draft, where I think that this is applicable to many of the multipath protocols discussed or standardized at IETF. So that the draft itself is still under development and some content is not finalized. However, you have got an idea today on which mechanisms about which mechanisms we think. And my question today is there any mechanism which is missing so far? And my second question is how to proceed with this draft. Do you see any value in that? Yeah, and with that, I'm ready for today, and now I would like to see some feedback.
Thank you, Marcus. I don't see anybody at the queue, and I don't want to spend a lot of time waiting, but I'll give it just 30 seconds if somebody wants to come up to the mic and offer feedback. In the meantime, I'll offer, Marcus, that to your question about how do you want to proceed with this draft. I think the one thing I would recommend is engaging the group on the mailing list and seeing if we can generate discussion. That's always a good way to get people interested. Andre is in the queue. You're up, Andre. Andre, we cannot hear you. I'm not sure what's going on there, but I...
to unmute myself. Can you hear me now?
Yes, go on.
Okay, sorry. Andre Bondi, Software Performance and Scalability Consulting in New Jersey. My question for Marcus is, how do you go about setting the adaptive expiration time? What are the variables that go into that? Is this something that you're going to do at connection setup so that you can establish what a floor on the latency would be? And how do you go about increasing the expiration time? Because if you make it too large, there's going to be an issue. And then there's a problem of degraded throughput if you assume that you have a longer latency on the slower pipe.
Yeah, very good question. Thank you for that. Short answer here. We have some implementation in the multipass DCCP available for that, and there we continuously update the timer with RTT information we get from the sender during transmission. So we have some signaling mechanism implemented for that. And second point, you are totally right. We have to set some boundaries, so it doesn't make sense to let the reordering queue grow to an infinite value. That would slow down the total throughput. So one measure could be here to set a manual limit.
Yeah. On the signaling, is that going to be in band or out of band? That is to say, along the connection, the payload connection, or on a separate connection?
Yeah, that is exactly why I think we need this draft, and that is a question which should be mentioned there, and then it's on the particular protocol to think about, should this be something which is in or out of band? So we would not give a final, or I don't see that we have to give a final recommendation to a particular protocol. That is, we just give some guidelines, and such questions you have put now, should this be something protocol specific or out of band or whatever, that then has to be decided within the particular working groups.
Okay, it may be service specific, just the way one uses out of band signaling for circuit switch telecom, SS7 for instance.
Oh, that is now very specific. SS7, from my knowledge, uses STTP, right?
Yeah, it just goes along on a separate trunk, actually.
Yeah,
this is old stuff.
Yeah, okay.
I mean, really old stuff, like
yeah.
20, 30 years ago.
Yeah.
I'm going to jump in here, Marcus. Let's take that question onto the chat.
Yeah.
Sure. Okay.
We do need to move on, but thank you for your questions, Andre. Very much appreciated.
Sure.
I'm going to move on to the next presentation, and thank you again, Marcus and Anna, for your presentations. I think we should continue the discussion on the list. Coming up next, BBR, Neil, take it away.
Let's see, can you guys hear my audio?
We can hear
my audio now? Okay, great. All right, so thanks, Jana. Yeah, we just wanted to give a quick update on the BBR related work that's going on in our team at Google. And this is joint work with my colleagues listed here. Next slide, please. So I think this will be a shorter talk than many of our recent talks at the IETF. Just wanted to give a quick update on the deployment status at Google. where we're nearing completion for internal TCP traffic. Give a quick update on the alpha open source release on GitHub, talk about some plans with respect to internet drafts, and then also talk about our continued work on what we're calling BBR.Swift. And of course, as always, we're just offering this in the spirit of offering our experience with these kinds of experiments in deployment. And of course, we are always looking for feedback or test results, issues people run into, any ideas or patches folks want to contribute would be great. Next slide, please. So in terms of the ongoing deployment of the BBR v2 algorithm within Google, for Google internal traffic, this is coming pretty far along. Right now, we're in the process of deploying BBR v2 as the default TCP congestion control for internal Google traffic. And we've gotten to a point recently where it's used as the congestion control algorithm for over 98% of the internal TCP traffic as measured by traffic rate or traffic volume. Just to be clear here, so for this internal traffic, we're using a number of different congestion signals. We're using the core BBR approach of modeling the bandwidth and minimum round trip time, but we're also using ECN and loss as signals as well. And as we deploy this, we're seeing some latency reductions at the tail for RPC traffic. And this is as compared to the previous congestion control, which for internal traffic was based on a shallow threshold ECN algorithm. And then we also have ongoing work for looking at BBR-v2 for Google external traffic, so basically YouTube and Google.com traffic over the public internet to end users, and that work continues. We're seeing some reduced queuing delays and reduced packet loss versus BBR-v1, but we're still not quite where we'd like to be, and so we're continuing to work on that. And of course, we're continuing to iterate in internal lab tests and experiments as well. Next slide, please. So in terms of the status of the algorithm and code, as we've mentioned at the IETF a few times before, we've got a release of the both the Iccrg and the Linux TCP code that's available. The Linux TCP code is on GitHub, and we've made a couple of recent minor updates to that code, rebased it onto a more recent version of Linux for those who are interested, and posted a few minor bug fixes. And we think the BBR-v2 alpha release is ready for experiments, and I think there have been reports, over the past year or two from other folks in industry and academia who have taken a look at it, both in production settings and in lab settings. And there are just some links in the slides to previous talks where we've given more details about the algorithm and the code and how it behaves. Next slide, please. So there have been a number of requests for updating the BBR internet drafts. The ones that are out there currently document the version 1 of the algorithm, and we are now planning to go ahead and update those to reflect BBR-v2, and our goal is to get those out there by the July IETF, so we can present those and discuss those. And the idea, I think, is to just replace the drafts that are up there with drafts that are targeting BBR-v2, hoping that will make it more clear that these are sort of replacing the earlier drafts. Next slide, please. So we did want to mention briefly that we are also continuing another thread of research work that we discussed briefly at the November IETF on an approach we're calling, for now, BBR.Swift, which basically leverages approaches from the Swift congestion control algorithm, which was presented at SIGCOMM 2020, where the approach basically uses the network round trip time as the primary congestion signal. And there, the main motivation is that it gives you, for environments where it's available, it can give you a richer signal with more information about the current degree of queuing along the path, which has sort of two advantages. One is that it allows faster reaction if there really are long queues right now. And then the other is that it allows you to help avoid overreaction when the queues may be persistent but might be short, for example. And there's ongoing work for that, preparing for production testing, doing some lab testing right now is the main focus. As we mentioned at TCPM, part of this research and development effort includes work to provide timestamp information in the TCP options to provide the sort of detailed, fine-grained, and more accurate round-trip time measurements that you need for a scheme like this. So there's a link to the extensible timestamp draft that we put out last fall. And ultimately, the goal is to allow this as an optional approach for contexts where the target network round-trip time is known, which might be the case, for example, in data centers. And also where cases, for cases where you know that the other traffic sharing your bottlenecks is using an algorithm of this same type. And this might be the case, for example, if you have separate quality of service queues and you can isolate this traffic to its own queue to avoid interaction with other classes of algorithm. And we do ultimately want this to be usable for physical machines and virtual machines, which will take some work to plumb the timestamp information up and down the stack to make these timestamps available, but that is kind of the long-term goal. Next slide, please. So just in conclusion, wrapping up, we're continuing to work on both BBR v2 and this newer approach, BBR Swift. And we're finishing the rollout for internal TCP traffic for BBR v2, continuing to iterate on external traffic or public internet performance. And we are hoping to release an internet draft in July. And as always, we invite feedback or test results, issues, patches, anything like that. And next slide, please. And I think that wraps it up. So if there are any questions.
Thank you, Neil. We have a few minutes for questions. I am going to try a new experiment this time, which is that I will cut off the Q&A in just under 5 minutes. Doesn't matter who's in the line. So I'm not going to cut the mic line, but I'm going to cut off the Q&A. All right, Omer, you're up.
Can you hear me?
Yes.
Thanks, Neil. Can you share, do you have any data on what kind of end devices BBR-v2 is deployed on for the external users? Are those Chromebooks, Androids, or something else? And what interests me the most is how BBR-v2 interacts with modern cellular networks. If you have that, if you have information to share, thank you.
Sure. Yeah. So to add some details there. So where we're deploying BBR-v2 for the types of traffic you're talking about is for the Google.com and YouTube servers that are sending traffic out over the public internet to end users. And so since this is basically talking about all of the users using YouTube and Google.com, or currently just some small percentage of them for testing, this basically should be a cross-section of of every kind of device that connects to Google and YouTube. And in our experience, of course, that's a pretty diverse set that largely, these days, I think largely the dominant bottleneck technology is Wi-Fi. But obviously we do have a lot of cellular users as well. On the cellular side, I think it's still mostly 3G and 4G, although we're starting to see, obviously some 5G trickling in now. So I don't have any numbers to share with you today, mainly because the public internet aspect is still a work in progress. But I can share that definitely we do spend a lot of time looking at the performance of both BBR v1 and v2 for users that have cellular or Wi-Fi connectivity, since that is such a dominant slice of the traffic for Google and YouTube. Excuse me. Does that answer the question?
Yes, thanks.
Oh, okay.
Anna, you're up. Anna, you're up. I don't know if you're unable to get yourself unmuted. And you're out of the queue. All right. Well, I will thank Neil then for his presentation, and I will. I won't speak for everybody here, but I'll speak for many people that we're very excited about the update to the draft. Looking forward to reading updates to the draft, to the BBR draft, Neil. And that is now. Oh, give me a second. All right, Gauri, you're up.
Hi, can you hear me?
Yes.
Excellent. Okay, so this short talk is going to look at zero RTT parameters for Quick, basically to exchange transport parameters to let you do something different in congestion control. There's a draft. It's at revision 7, and it's with these people on the slide, Nicholas, Emil, Tom, and me. Next slide, please. So this is a draft that tries to deal with paths which are not typical. So we're talking about paths that have something that's different in them. Maybe they're slightly higher in delay. That could be many tens of milliseconds, could be many seconds. They maybe have a very large bandwidth delay product. They maybe have a sub-IP layer that is on demand, and therefore when you resume a connection, you get a different capacity, or maybe you usually get the same capacity, but sometimes you might get a different one. And these paths are typically also have other optimizations, such as asymmetry improvements to get their overall efficiency at an acceptable level. If you have paths which are non-typical, then there's two options. Either you dynamically learn that the paths are non-typical, or you have information that lets you customize the protocol stack to make it work. And you can do this to mitigate the effects of delay, the BDP, capacity, asymmetry. Our focus was primarily on satellite paths. That now covers a very wide range of paths, and we focus just on geo in the initial work here. But you might see other paths that have similar needs. And I think that's one of the important things I'd like to kind of bring up here is if other people are seeing paths that have other needs, maybe slightly different characteristics, we'd love to talk to you, because we'd love to make sure whatever we propose here actually works on across a variety of different paths. Next slide, please. The context is to define some transport parameters as extensions to Quick. And these are shared during the 0 RTT phase, basically allowing resumption using additional transport and connection properties discovered from a previous successful connection. And this is a lot like TCP control block sharing, but it's also different because it's designed for Quick. We hope that the information that's provided is useful for optimizing client requests. There are cases where your web browser automatically prioritizes different pieces of information. Maybe for the web client, that's a well-known bit of technology that many vendors have already have in their products. But for other applications such as Dash, and probably for VPN applications, etc., there will be ways to optimize the way in which the network's used by the clients. Since this is ICCRG, the core thing we're going to talk about is using the information to make a jump in the CWIND, the congestion window, so that you, instead of starting a session with a configured large initial window or with a normal small initial window, you choose something which is based on previous history and use that to initialize a safe CWIND. And like any other method that's used with TCP, for instance, we'd like this information to be shared across multiple connections. This is not a new proposal, but it's a proposal which we'd like to make concrete for Quick. Next slide, please. Why is this important? If you have the sort of BDP and delay that you might see in a satellite geo environment, then it might take you many seconds to download something which you could actually send using TCP in maybe a small number of seconds. So Quick is adding maybe 2 seconds of extra time in a typical configuration here, simply because there is no PEP involved optimizing the protocol. So maybe we can do much better. And this slide shows 2 methods which could be used to improve performance that we've tried in a spreadsheet analysis using a little tool we have to look at different combinations of parameters. We see the orange one is a jump to 25% of the last window, and then 2 rounds of RTT to get to the full size window, and green, a high jump method where we delay it by 1 RTT. So we make the jump more conservatively. There's a range of options in the orange-green area, all the way across the blue area, where you can trade performance against conservative congestion control behavior. And that's the good reason for presenting this in ICCRG, because a lot of the issues are concerned with how best to adapt. But before you adapt, you need a method of having the data about the previous connection. Next slide. And the way in which to have this information, we believe, is to get the server to store parameters in a BDP extension, which we then communicate from the server to the client. The client gets visibility of the information. It may also get an encrypted token. The encrypted token can be returned back to the server, so the server could be stateless if that's the design you want, and simply receive previous information about a flow that it had previously struck with the same client. When you come to the second connection to the same server, you can reinitialize the information. And of course, there's a possibility that the path to the endpoint could have changed. And there's a path change possibility in the amount of capacity that you might have. Of these 2, the most dangerous is the change of the path. But the method we propose will validate the RTT against the previous RTT. And we're suggesting that we include some form of pacing when we initially start a new higher congestion window. And in this way, if there is a big RTT change on the path, then the damage that's created is very much limited and we believe could be made safe for wide-scale deployment, and therefore something that might be interesting to standardize. Next slide, please. This is the set of metadata we expect to put in the BDP metadata. 3 parameters, bytes in flight, minimum RTT encountered, which is partly to configure as a safeguard, but also to configure a pacing interval. One of the problems is initializing the RTT of the pacer. So this information is quite helpful in getting a good response, and the maximum packet number encountered. So we say with these 3 pieces of information, can we now jump safely? Next slide, please. Next slide, we don't need to talk about this. Well, we've approached this in various ways. One way was to perform some implementation work in PicoQuick, and there's a GitHub that you can use to access this. This is primarily focused on the exchange of the cryptographic information at the start of a quick connection, so that you can actually get the bandwidth parameters exchanged. And it focused on a very simple, easy to implement change to the congestion controller. We have a more advanced version of how we expect that congestion control update to occur in the draft. So please look there to find more details about what we actually suggest. But it's clear, even from these 3 simple results, that without the option, it took 4.3 seconds to exchange the 2 megabyte chunk of data on average. That's the median value. With the 0 RTT enhancement, 3.4. And with the 0 RTT BDP, 2.9 seconds. So at least saving what we would see as people evaluating satellite links, a significant proportion of the download time. And these are for modern satellite links running at 50 megabits per second. Next slide, please. Worth also looking at how the client might use this information, because the server can always optimize, and it'd be nice if it optimized in a predictable way so that the user didn't have to be concerned about it. But also there's a possibility to optimize the client if it knew about the likely BDP aspects of the path it's using. And we did some work in 2018, which is published in the NetSat Days conference. It looked at Dash, and we showed that using a Dash client, we could take this information as one of the inputs to adapt the results to produce a much more predictable performance. In this case, trying to avoid the strange behaviors that happen when your predictor gets the capacity wrong, and therefore vastly underestimates the amount of capacity you've got because you've got a larger RTT. There was talks in the IETF Open about the various ways in which dynamic adaptive streaming players can play out, and this is kind of like one of the input parameters, and a good example of how knowing something at the client can help you actually make better requests at the application layer. Next slide. This shows a number of different plots all on the same graph. I'm first of all going to talk about the blue plot. This is Reno. The Reno behavior is that the congestion window opens in more or less steps, stepping up each time it gets a round of acts. And for a longer RTT path, this basically controls the amount of capacity you can get. For small to medium sizes of exchange, this is totally the dominant factor rather than the amount of bandwidth available. When you use something like Quick, because if Quick uses Reno, there is no protocol enhancement along the path. So if we look at the jump scenario, we see here a different case. This is where the congestion controller is initialized with a previous RTT measurement. We chose in this case to initialize with 25% of the bandwidth. That's 25% of the previously used capacity. That means the following RTT, there's a step up to use half the capacity and then another step up, etc., until after several RTTs we've used the whole capacity. Now, it would be possible to jump immediately to use the full capacity, but if you're a congestion control person, that might frighten you because it would cause severe congestion against any other flows that happen to be present at the time when your new flow started, rather than when you previously measured your available capacity. So we decided to initialize to around 25%. Again, something we're happy to experiment with, and there are ways of making this more conservative. We know this. Next slide. A slight variation here. I'm going to talk about the pink and grey curves. The pink curve is a method we call high jump, which delays the increase, and we can talk about more of this in the draft. We also have high jump pace, the grey curve. What I'm trying to say here is that there are a range of congestion control decisions, all of which are safe to some extent. We would claim safe enough, and a much better performance than Reno. The high jump pace paces the packets out at the rate determined by the previous capacity, and we get this more linear growth in the use of the capacity. And we could talk more about that, but I can't because I need to move on. So next slide. We talked about the client being able to use the information. So this is not just a server-side decision, which is why we're trying to standardize the format of the transport extension. Next slide. And we've also looked at the security of it, the way in which to exchange the parameters, the way in which the path cannot modify these parameters are important to us. And we believe that we have a safe mechanism here that works with TLS 1.3. Next. There's some interaction. Emil is our TLS person, and there are probably things that we should discuss between Quick and TLS to see how this initial exchange of data should best be handled. I think some form of synchronization between the two working groups is important. This isn't a congestion control issue, it's more a security discussion, but it's still an important part of the design of the mechanism. Next slide. Congestion control safety is the thing which probably is most important for this group, and if we can standardize or adopt a way of exchanging this information, we also need to adopt a way of safely using it. We're assuming that any method we use here will have a way of backing out quickly and efficiently as soon as there is loss detected and the CWD has been artificially increased. So we will expect to quickly back out of any problem, but do we need a draft on congestion control safety that updates 6928? Maybe this might be something useful to set the boundaries here. Next slide, please. We could use a new BDP extension specified in Quick, and we are wanting to do that part of the work in Quick, but there's obviously also a congestion control piece, which is why we're trying to bubble this up here in this group and attract some comments. So trying to stick roughly to time, I'd like to take comments now if possible.
Very quickly, can you mute your mic there, Goy? So I don't know that we have time for Q&A. We are already at time. But I'll encourage people to, thank you for presenting this here. I want people to engage on this question, and I'll take my moment to basically say that this is something that we expect leave aside a specific mechanism, but the idea of recording and reusing congestion control information is something that we expect will happen in Iccrg, because there are places to store this information at the client. This is something that is different from TCP, where a server can actually encode this information and ship it off to a client and then use it on the next connection when connection is established, which makes it much more likely that something like this will get deployed by Iccrg implementations. So it is much more important now that we actually engage on this topic. ICCRG is the right forum. Perhaps we can continue this discussion on the list and at subsequent, at the next meeting as well. But I'll thank Gauri also for putting this together very quickly at short notice. Do you want to say something, Gauri?
Yeah, I'd just like to say that we are super interested in not doing this as a group of satellite engineers who've worked on PEPs and enhancement and modeling of really long delay paths, but to do it within the IETF, where we can get other people involved in this. This is a super interesting place where we can actually collaborate between different people, and we'd really love to get feedback on this.
Thank you so much, Gauri, again for the presentation. One quick announcement. Bob just announced that a new draft describing Prague congestion control has been posted. Please take a look. We might end up discussing that at the next IETF, the next ICCRG meeting. Thank you again, everybody, and enjoy the rest of the IETF. We'll see you next time.